Hello and welcome to the presentation of our workshop paper, Designing a Collaborative Virtual Reality System to Assess Social Inclusion Among Neurodiverse Students. I will begin by introducing the project and our motivation for taking this approach. Neurodiversity refers to variation in a human brain, for example within a group of individuals. We distinguish between variations as divergent or typical, while acknowledging that further work requires more detailed descriptors to understand the needs of our users regarding the design of the VR system. As of now, the following presentation will present and discuss the concept of enabling interaction between interpersonal relationships between neurodiverse individuals through collaborative play, which is partly defined as an individual's experience of social inclusion. Experiencing social exclusion has been linked to a decrease in well-being through stigmatization and discrimination, while the contrary, experiencing social inclusion, has been observed to result in improved happiness, self-esteem, confidence, and mental health. Another implication of a lack of inclusion in the context of school attendance is the decrease in social skill development. This consequence was of interest to the project group. How can we use VR to eliminate barriers to social inclusion and promote social skill development that may affect group dynamics experienced in real life? The project group consisted of researchers from the Multisensory Experience Lab and professionals from the Danish company Specialisterne, whose primary objective is to build bridges between neurodivergent individuals and the job market. To further refine this idea, we started to investigate traditional methods in the field to gain an overview of the opportunities that VR may present. Traditionally, the social outcome of inclusion interventions has been researched in the field of sociometry. Sociometry has been established as a reliable methodology to assess and map social relationships in a group. However, the method relies on self-reported social preferences found by asking individuals about choices in social situations. For example, who would you like to sit next to in the bus? We found this to be interesting as VR presents many more data points for observation on implicit behavior in social situations. We were interested in understanding how VR can support the training needs of both neurodivergent and neurotypical users. We found positive prospects on the use of VR to train neurodivergent users' executive functions, communication, social skill development, and what is referred to as daily living skills training, an important set of skills of neurodivergent individuals to gain independence and increase well-being. We also found positive prospects on the use of VR to represent and interact with more advanced and abstract concepts in mathematics education, a task relevant to neurotypical individuals. Moreover, interesting research on group dynamics in VR informed us about the range of emotional states that users experience in VR, which was found to be similar to real-life face-to-face experiences. This phenomenon supports our premise that the social interactions and skill development in VR may be transferable to real life and thereby change or overcome issues related to social exclusion in a group of individuals. This led us to the aim of designing and implementing a VR system that allows neurodiverse students to engage in collaborative tasks of varying difficulty for the long-term purpose of studying inclusive behavior in a school class. We chose to combine the DLS training scenario of supermarket shopping with the balance model for teaching mathematical equality. Moreover, we implemented verbal communication through voice over IP and nonverbal communication through mapped body language using inverse kinematics. Finally, an additional support module was implemented in the shape of a wristband with two options for visual and auditory help sequences regarding the objectives and tasks of the virtual environments. This was done to allow students to receive help regardless of the situation and to log the potential support preferences of users. So, in regards to the situation at hand, we designed the collaborative task to involve several sequential tasks involving various types of products and shopping mechanics allowing users to execute the task. At the entrance of the virtual supermarket, users are met with a shopping list of 5 products. The products require 2 types of actions, either finding the product and collecting the right number, or measuring the right amount by using the virtual balance. This collaborative task was part of 2 additional virtual environments. As you can see here, the flow of the 3 virtual environments was as follows: select avatar based on user preferences, introduce concept related to tasks of virtual supermarket, and perform collaborative task of shopping in the supermarket. 10 pre-made avatars were selectable by users. To visualize the avatar to users, a mirror was implemented, and in order to adjust the scale of the avatar to the users, a button for recalibrating height was implemented. When a user was satisfied with their choice, they could press the button for entering the virtual classroom. The virtual classroom was designed to resemble a traditional classroom and included props and concepts from the supermarket. The idea here is that a teacher can use this virtual environment to slowly introduce the elements of the collaborative task before entering the virtual supermarket. Additionally, a task pad was implemented in this virtual environment to introduce the use of the balance model to measure amounts and figure out the weight of objects through mathematical equality, as the deflection of the balance pans depicts. Finally, we have the virtual supermarket. As seen on the 2 overviews, the supermarket includes different sections with different types of products, being the butcher section, processed foods, refrigerated goods, and fruits and vegetables. As seen in the picture on the left, users were met with a shopping list depicting a thumbnail of the products, the number or amount, and the name of the product. Next to the shopping list, a shopping basket could be found, allowing users to collect items for easy transportation around the virtual supermarket. On the picture on the right, the virtual balance can be seen. Users can measure amounts by placing weights on one side and products on the other. By reading the deflection of the balance, users can determine whether products weigh less, equal, or more than the placed weight amount. After determining the correct amount, users can place the fruits or vegetables in a plastic bags, creating a single entity of the product for easy transportation. Finally, after finding and gathering the products requested in the shopping list, users can approach the self-scanning register to scan, pay, and purchase the products. Here, users are met with a display showing the scanned items, the total price of the purchase, and the remaining price. A wallet with Danish coins and notes appears next to the register, and these can be dragged into the money slot of the register. If users make mistake, they can choose to clear the list or delete the latest scanned item. Finally, when items have been scanned, placed in the shopping cart next to the register, and the purchase price has been matched, users can push the pay button, and depending on whether the shopping list has been partially or fully completed, a rewarding sound and confetti animation will be played. Based on this design, we conducted an exploratory study with 8 users, being 7 neurodivergent students and 1 teacher, which highlighted several design issues related to the collaborative mechanics of the VR system. Although the audio of verbal communication was spatialized to attenuate direction and distance, users requested additional visual cues for the communication. This could be done by artificially highlighting avatars currently speaking, or to implement further facial expressions related to the speech output through mouth animation. These cues were requested by the users to easily determine who is talking at any given point. The VR system has a selection-based avatar system, which currently does not allow for fine-tuning to a user's personal appearance. We believe that future iterations of the system should extend this system to allow for better customization of particular features of the avatar, or perhaps implement an additional step in the VR system's pipeline, allowing teachers to take images of users and generate avatars. A number of commercial solutions are available for this particular purpose. The group of individuals that were participants in the test were all relatively comfortable and excited with the novelty factor of VR. However, it is our hypothesis that for other groups of neurodivergent users, reducing anxiety is a crucial component to the experience. We believe that safety measures such as proximity monitoring, as seen in VR chat, and environmental changes could be used to provide users with a safety mechanism in situations that they feel are uncomfortable due to the uniquely dynamic social situation that can occur in such an experience. In regards to measuring the outcome in larger scale future iterations, we outline how short-term effects on simple measures such as procedural knowledge and competency development can be used to assess the VR system's capability in conveying educational material to users with varying needs. As a result of the obtained knowledge and skills from the educational aspects of the VR system, we may also observe effects on neurodivergent users' experience of independence and well-being in regards to how their DLS have changed after the experience. However, as a main objective, the aim of the intervention is the social outcome. Here we are interested in how the VR system's data logging and mapping can be used to generate reports for teachers in various forms. For example, the obtained data of social and collaborative interactions may be reported to teachers in the form of a sociogram, which is a graphical representation of social relationships in a group of individuals. This outcome is therefore twofolded. How can this new insight be used by teachers to assess and intervene? And how can the effect be observed individually in regards to well-being from experiencing social inclusion after the intervention? The teacher's report obtained from the VR system can include multiple measures regarding the group dynamics and individuals of the group. As of now, we see them as social and collaborative interactions and as personal preferences and performance. We believe that rich social interaction may result in observable affective actions, such as gestural greetings, verbal laughter, encouraging instructions, and collaborative actions, such as handing over objects, role-taking, and so forth. Moreover, to emphasize and discover links between individuals, we may observe on other dimensions to these interaction types, for example, directivity of communication, frequency, and performance logs. As a request from teachers of the institution we collaborated with, there was also a clear interest in learning more about the participating individuals to further profile their behavior and preferences. We see this as an opportunity to use the support module to exemplify whether or not a user prefers auditory or visual cues while learning. However, we believe that this module needs further work in order to support this idea, as the cognitive load may differ. To observe the engagement level of individuals, we are planning a simple logging module that tracks and calculates the engagement of an individual in regards to their activity level. How many times do they grab objects of the environment, and how many times do they push buttons or other interactive elements? This may also be used to assess the role-taking of the individuals by planning out and designing particular mechanics to certain roles of the collaborative task. To conclude, we have presented a VR system designed to promote collaboration between neurodiverse individuals by combining DLS and math training tasks. Based on a preliminary and exploratory study, we presented initial findings depicting several design issues regarding the collaborative mechanics of the VR system. And finally, we presented our considerations on how such a system can be used to assess inclusive behavior and report findings to teachers to learn more about the individuals and group dynamics of a class. Finally, we see the future work of the project as follows. Firstly, we need to reiterate the design by overcoming the issues found in the first test. Thereafter, we need to embed and test the data gathering module for behavioral observations, and finally conduct a larger scale long-term study in close collaboration with a class and their associated teacher. Thank you for listening to our presentation.